and then talking about what you can, well, there's not really anything you can forget for the final, but reminding you everything you need to remember for the
formulas?
Huh?
So all the formulas that we need to know before?
We'll go over what needs to be in your brain and what is provided, and I printed the reference sheets that you'll get with the final, and they're on my desk. So I will post that so that you see exactly what's there and exactly what needs to be in your head. But yeah, we'll go over that. So first, I'm going to go through the example on 621, the very last thing in the course pack. One more pressure vessel problem that does sort of nicely illustrate a couple of these last concepts, the principal stresses, failure criteria, et cetera, et cetera. So using the pressure vessel that we did, in fact, use in lab. It is this nominal diameter of 9 inches. And instead of with the lab, where we measured strain, calculated stresses, and then used those pressure vessel relationships to get a thickness, we're going to say, okay, we think or we know that it's 14 gauge steel, which has a thickness of 0.747. Let's look at it the other way. Let's say how much pressure can we put in it before we expect failure. So the first thing to parse out is if we're doing a failure analysis, what do you have to make sure that you're working with? Can you use any old arbitrary sigma x, sigma y stress state? You have to find principal stresses before you can evaluate failure using failure criteria at all. And if you're looking at failure criteria and you want to know where is it that I get to yield, what do you know about that state? That your factor of safety is 1. So that's the trick that's going to let us do this. That we're going to evaluate the case for a factor of safety of 1, and we know we have to use principal stresses to do this. So what's the other trivia about pressure vessels that we know? We know that we know they have expiration dates, and I still need to email Bruce about that. We know that in the hoop direction, a cylindrical pressure vessel has stress PR over T, and we know in the axial direction that that's PR over 2T. If we've got a spherical vessel, what's different? It's the same in all directions. The same in all directions. So this way, we've got hoop in one direction, axial in the other. And if we need to think about this in terms of principal stresses, what do we got going on? What's the third principal stress? What's the third principal stress? Sigma C is always. So we know that there's a third one floating out there is 0. And if we draw this arbitrary stress state in a pressure vessel, what do we have going on? We have hoop in one direction, that if we're blowing up the pressure vessel with positive internal pressure, we know it's stretching this way. We know it's stretching, and I guess I should reverse these, but it doesn't really matter. One's hoop, one's axial. And how much shear is there in a pressure vessel case? By default, there is no deviatoric. Think about a balloon. What does a balloon do? It just gets bigger. There's no shifting, there's no twisting, there is no shear. So tau is 0. And what's the definition of the case when you have principal stresses? If we were to draw Moore's circle, what's the first point that we put on Moore's circle? It's our x stress and our tau xy. So if you have no tau xy, what does that tell you? It tells you you're on this axis, and that means you are already at principal stresses. If the shear is 0, those are principal stresses. If the shear is 0, those are principal stresses. So this is sigma A. And how do you know the difference between sigma A and sigma B? Sigma A is the bigger one. And so this one is sigma B. How do I know that? Because it's half as big. Because it's half as big. So that's my sigma A, that's my sigma B. What's my sigma C? In plane stress, he's always 0. Okay, so for a pressure vessel, for a cylindrical pressure vessel case, you know you've got principal stresses already. Why? Why? How do you know that? Uh-huh. How do you identify the fact that you've got principal stresses? No shear. Thank you, Mr. Brock. No shear. Tau xy equals 0 means principal stress. Okay, then now all of this failure, so I've got a sigma A out here. For a pressure vessel, you know that sigma A is positive and sigma B is positive, right? Because they're both being stretched. And our good friend sigma C is 0. For these failure criteria, we've got two different ones that we're really going to use. We don't really use maximum principal stress. We use maximum shear stress, otherwise known as Tresca, and we use maximum distortion energy, also known as von Mises. So let's start with the max shear criteria. How do I get that factor of safety? It is the yield strength of the stuff, wow, that's an S sub capital Y, over what? 2 times tau max. That one is going to be provided. That's on the will be provided list. The failure criteria are provided. So your max shear factor of safety is this yield strength over 2 times tau max. But how do I get tau max? This one needs to be in your brain. Okay. Well, we got sigma A and B. What do we need to do? Reorder according to size. Well, it just so happens that they already are, right? So this is sigma 1, this is sigma 2, and that's sigma 3. Okay? So to get my max shear stress, I'm going to have sigma 1, which is PR over T. That's supposed to be a T. PR over T minus sigma 3, which is 0, over 2, so I'll just throw that 2. That ends up being the axial stress. But that is the max shear stress.
So what do I know? I'm asking for the pressure. That's my unknown. I know the radius is half this diameter. The 2 is 2, and I'm going to assume that the thickness is
0.0747. So I know everything but the pressure. So I can solve this tau max in terms of the pressure. So tau max equals, all of these are just numbers, so I end up with 30.12 times the pressure. And then what did I say? If I expect to get to failure, my factor of safety is 1, so that equals yield strength over 2 times tau max, which is 30.12 times the pressure. And the problem statement tells me that the yield strength is 50,000, or the pressure at an expected yield is 830 psi. So if our thickness assumption is right, and if the yield strength of the material really is 50,000 psi, we should be able to put 830 psi into that pressure vessel and be good to go. Now, it's expired, so I don't know if we really want to do that or not. I wouldn't really want to hug that close on the edge of material yield either, because that puts trust in the welds, that puts trust that it hasn't been dunked or dinged or rusted or anything. But we also don't have a compressor that can do more than about 85, so we're probably good. So this is what we expect to be able to put into it using the max shear criteria. All right, let's look at the same analysis with the von Mises criteria. Von Mises, also known as distortion energy. Okay, that's the one that's the more complicated. We have to find the von Mises equivalent stress. That's your sigma prime. That formula will also be given. And sigma prime is, in fact, the A principal stress squared minus a cross product of the principal stresses plus sigma B squared. But now hang on, we already figured out that these hoop and axial stresses are our sigma A and sigma B, right? So we can just substitute these guys in for sigma A and sigma B. So that's going to look a little something like this. PR over T quantity squared minus PR over T times PR over 2T plus PR over 2T quantity squared. Well, we can do a little factoring. I think all of those terms have a PR over T squared. So we have the square root of PR over T squared. And then if we see what's left, we've got a 1 minus a half plus a quarter left in the rest of those terms. So PR over T quantity squared leaves a minus a half there, and square a half is a quarter, so plus a quarter there. Just a little bit of algebra magic. So we can take the square root of PR over T squared, and we get 3/4 still under the square root, and PR over T out from under the square root. So that's the von Mises stress. And okay, so with the von Mises stress, what's our factor of safety? Our factor of safety, N, is just the yield over that von Mises stress This von Mises stress, again, we know the radius, we know the thickness, that's left as the only unknown. So this ends up being 52.17 times the pressure. So 50,000 over 52.17 times P equals factor of safety of 1 for yield, gives us a pressure of 958 psi. So again, if you remember from the plot with our different factor of safety envelopes, the von Mises, the ellipse, is a little more conservative than the polygon. It's a little further out. So what does that mean? The tank is rated for 160. So that means that the ASTM pressure vessel code implements a working factor of safety of about 5 or 6. So actual factor of safety N is about 5 or 6, which is typical for pressure vessels. So that's a wrap. I'm not going to put 160 psi in it. All right. I am sure not going to put 800 in it. I wouldn't want to be anywhere near anything with 800 psi in it. All right. Questions on that? All right. A last review. Or I guess maybe I'll bring up, let me see if I can connect to my drive and bring up the document. I will post. Oh dear. In the compression in the cylinders? I really don't know. I don't know enough about it. I don't know what a peak instantaneous pressure would be.
But that was a Pascal. It's like 200 meg.
I bet there's more pressure.
Oh. Anyway. All right. Back to our review of everything that we've done. What's part 1? Plain old axial loading. What do you got to remember from part 1? Plain old normal stress. If you have an axial loading case, it gives you normal stress. It's equal to P over A. If you have simple uniaxial tension, you want to know how much something stretches. How far does it stretch? What is that guy? That's our PL over AE. If we have stress and strain in a one-dimensional stress situation, in an axial stress situation, what's that? How do those relate? Slope of a stress strain curve is Young's modulus. So we know that stress is Young's modulus times the strain. What's our plain old one-dimensional definition of strain, general definition of strain? That's the one. And also, it's usually a good thing to remember that my new length is my length plus my change in length. I might ask one like that. If you have a strain of blah, how long is the wire? What's the new length of the wire? What else has got going on? If I pull it this way, how much does it shrink this way? What's that relationship governed by? That's Poisson's ratio. That the transverse, the negative ratio of transverse to axial. How can you remember which way that goes? How do you remember which way that goes? You know, with your sensible selves, that if you pull on something this way and it gets longer by an inch this way, it is not going to get shorter by 3 inches this way. It gets shorter by 1/3 of an inch this way. So you know that the ratio has to set up with the axial being the bigger number, and for metals it's usually very roughly 1/3. So you know that that's the transverse, that the transverse shrinks about 1/3 what the axial grows. Use your common sense. What else do we need to know out of part 1? That pretty much covers part 1. So what kind of stresses do we get under axial loading? We get normal stresses. All right. In the most general shear case, how do I get an average shear stress? That's just a V over A. If I have a composite cross-section, like one of these pesky stacked up boards like this, and I guess I want this all on here, so I'm going to go on here. If I've got one of these pesky composite cross-sections, and I want the shear at a particular location, what do I go for then? It is that VQ over IT. And what's my Q? That's a pesky guy. Q is this second moment of area, and it is, you think about it in terms of the area that would shear. If I ask you for what is the shear here in this center joint, Q is A prime times Y bar, where that A prime is the area that would translate, and the Y bar, several different Y bars in here. This Y bar is the separation distance from the centroid of the whole thing to the centroid of the part that would be shifting. From the centroid of the whole thing to the centroid of A prime. All right? So that deals with your linear shear forces. We can also have our torsional shear forces. So applied torques, what kind of stress do those cause? Shear stresses. And what's our formula there?
TC over J.
That's the one. I guess we forgot one guy up here on this linear shear thing. This is our normal stress-strain relationship. There's also our shear stress and strain relationship. So this guy is your Young's modulus, that guy is your shear modulus. All material properties will be provided. Okay, so this is my shear stress. How about if I ask how much it twists? Which guy is that? That's this guy's cousin, and it is TL over JG, and what's my symbol for that guy? Is a phi. The angle of twist. So this is my normal stress. This is my linear deformation. This is my shear stress. This is my angular deformation.
What's gamma?
Gamma is the shear strain. It's the change in angle of what would have been the corner of your material. All right. So what else is going on in here? Let me check my Post-it note for reference. Yes. Gamma is, in fact, in radians.
What about phi, though?
Yes. True. Also true. Oh, we forgot a very, very important guy up there in the linear. It is the temperature one. It is the temperature one. We may have to deal with temperature change. What is the temperature change effect? The temperature change affects the elongation. So, PL over AE and the alpha delta T times the length term. Okay. We've also got, so bending. Bending causes a bending moment M. What kind of stress do we get from bending moments? We get normal stresses, and generally it is minus my over I, where y is what? Distance from neutral axis. If we have a nice, easy, symmetric cross-section, this guy can simplify to sigma equals plus or minus MC over I. Now, the other thing from bending that we know is this. The bending moment is equal to the bending stiffness times the second derivative of the deflection. Guess what? That means you get to see it again. You get to do a couple more integrals before you're done with it. So this deflection can be tabulated for nice simple cases. You will have the beam deflection tables as part of the reference. You will also have the discontinuity terms as part of the reference. So I can, just like before, I can guarantee that there will be one that you have to put it together and integrate it twice to get the elastic curve and tell me what the deflection is at a particular point. And I can guarantee that you will have to use the deflection tables to pick one of the simple cases and probably use superposition to say, oh, well, I've got a point load here and a point load here, and I can add them together. Or I've got a distributed load and a point load, add them together. So deflection of beams by the brute force method and using the deflection tables. Thermal expansion, principal stresses, pressure vessel. This last problem was a good review of pressure vessel. Pressure vessel, what is the main take home? The fact that if you have a pressure vessel state, pressure vessel inflated to some pressure, how much shear stress do you have? You have none. What does that mean? That means that the stresses developed in a pressure vessel are principal stresses. And because they're both positive, you know that they are sigma 1 and sigma 2, and that sigma 3 is 0, because they're both positive. What else? In terms of the format of the exam, there are no pesky essay-like questions. This one is a bit more cut and dry. In terms of content, it's about half stuff that you've seen on exam 1 or 2, and it's about half stuff that you've seen since. So it's weighted more heavy, since there have been fewer weeks since the second exam. That stuff sort of counts more. From the new stuff, guarantee you will need to be able to draw and label a Mohr's circle appropriately graphically. You also need to realize, and I guess I can scoot a little bit, so draw and label Mohr's circle, identifying a stress state. So if I just draw something that looks like this, that says, I don't know, 10 megapascal, 18 megapascal, and 30 megapascal, what do those things mean? How, if I say find the principal stresses, you know what to do with that. Or if I say draw Mohr's circle, you know what to do with that. So what do you do with that? You know that Mohr's circle, or that the principal stresses, sigma A, is sigma average plus the radius, sigma B, that's an A, is sigma average minus the radius. What is sigma average? Sigma average is, well, it's the average. Sigma x plus sigma y over 2. What's the radius? The radius is that Pythagorean distance. And it's important that you remember that it's not sigma average in here. It's the difference term. So that's your Mohr's circle geometry stuff. So this is an arbitrary stress state. These are what? These are your principal stresses, sigma A and sigma B. The failure criteria, that's just essentially knowing what to plug into the formulas. For the max shear stress criteria, max shear stress criteria, what do you need to know? You need to know tau max, and tau max is what? Sigma 1 minus sigma 3 over 2. What's the difference between sigma ABC and sigma 1, 2, 3? Just the order. Anna Michael Jackson song. A wording detail. I can guarantee that you will need to draw a shear moment diagram. That's an old one from the second exam, but it will come back. You will have to draw a shear moment diagram. And the wording, understanding the difference, if I ask you for what is the maximum shear or what is the maximum magnitude. So one of them might be a positive or a negative number. The other one is the absolute value. So if I'm asking for the max magnitude, you take the absolute value and just give me the biggest number. If I just ask you for the maximum or the greatest moment, I might be asking for plus or minus. Just pay attention to the wording. And also, I guess, pay attention to the answer sheet, because if I'm asking for the magnitude, I probably will have the absolute value dealios down in the answer block. Thermal expansion, combined loading, I'm going to talk about in a second. Understand principal stresses. Pressure vessel we talked about. Plain old strain. Max value versus max magnitude. Bending moment is the second derivative of deflection. All right, combined loading. So understanding how to get from some loading scenario to that arbitrary stress state drawing, our little cube of material. So let's say I have a case that's looking a little something like this, and it's a circular pipe, and I'm going to have some torsion, and I'm going to have some compression. So I've got a torque and an axial load F, and what am I going to have going on? What kind of stresses would I have going on in this thing? What do I need? Let's start back there with Mr. Beasley. What's one of them?
We have torsion.
What kind of stress does that make? Okay, so that's going to be some, what's my formula? I'm going to have some TC over J, and I'm also going to have some what? I'm going to have some sigma, and that would be, it would be a P over A. Now I can't just figure out those numbers and add them, because they are apples and oranges. I have to draw a stress state. And let's make it a little more interesting. Let's throw a load on there, and we'll call it, I don't know, we'll call it F2. But what kind of stress is that guy going to make? It's going to make some bending stress. What kind? That's that guy. How do I calculate? Let's assume it's a symmetric cross-section. So it's MC over I. And it's going to be some tension there and some compression there, right? Okay. Refreshing our memory, what all along have we said this coordinate has been along the beam, has been our x coordinate, right? So now let's think about drawing, and this may be helpful to your combined loading projects as well. Let's think about a little cube of material up there at noon. Okay? What's going on at noon? And I'm going to try and do some color coding. We're going to have this guy is blue, this guy is red, and this guy as green. Okay? So if I'm up at noon, do I have tension or compression in my blue? This guy, this is my noon. Okay? So that is going to look like this in my x direction, right? And it's going to be a plus MC over I. All right, what am I going to have? How do I need to draw my red, Stephanie? Well, that's this guy. So is that tension or compression? It's compression, and it's in the same direction. So that's going to look like this, and that's a P over A. Okay, is everybody with me that those two are in the same direction, that those stresses are collinear? That one's a tough one to wrap your head around because this force is downward, but it's causing the stresses in that x direction, in the long axis of the thing. So both this guy and this guy are stresses in the x direction.
How can you add this together if at the neutral axis there's not going to be any
because
moment.
that's true. Okay?
But it doesn't.
Hang on. Okay? This guy is at noon. If I were to draw, and this is a little bit of a sidetrack, but if I were to draw my little cube of material on the neutral axis, what would it look like? It would look like all that guy, all P over A. What is my sigma blue? 0. Does that answer your question? Okay. So now the one that we haven't put in the mix yet is our green. Our shear stress is a TC over J, and if my torsion is this away, and it actually doesn't end up mattering which way you put it, but we have TC over J in shear. And this is a plane stress case because all of this is in the X plane. How much Y normal stress do we have? How much Z normal stress do we have? None in either case. We got no Z, we know that because it's plane stress. But there is no smooshing in this direction, so there is no Y normal stress. We have no smooshing in this direction, so there is no Z normal stress. We have bending, but that gives us X normal stress, not Z normal stress. Actually, and I don't want to confuse anybody, you would, in fact, have a little bit of Z stress locally because of that actual force in the real world pushing down on it, but we're not dealing with that in this class.
That'd be Z or Y.
That would be, in the way we've done our coordinate system, that would be a Z.
Okay. Is Y end of the board?
Yeah.
I don't understand why the FBI is on the X axis.
Okay, push down on this. Where do I get what are the forces of the magnets? Which direction are the magnet forces holding the pieces together?
The magnets are in the
Right. Okay. So you can think about it like these little molecular magnets are trying to hold the stuff together. And in which direction is that making tension on the top? In the X direction. In which direction is that squooshing them together on the bottom? Like compression? Does that help? Yeah. Amazing that I had a stick of magnets with me. So yeah, that's why this guy causes normal stress. Because those little molecules are trying to hold on to each other, but you're stressing them. In fact, you're giving the molecules stress. So that's what the stress state looks like. That's your arbitrary stress state. So you add this P over A and the MC over I as appropriate. Now, what would the 6 p.m. one look like? If I come draw my little cube, and y'all know what I mean by the noon and the 6 p.m. one, right? A little piece of material. If I look at it this way instead, if I look at a little section at noon or at 6 o'clock on the cross section. So this is my noon part, this is my 6 p.m. So how does this guy look different? The big difference is that both of them are compression. Both of them are both of the normal stresses, both of the sigma X stresses are compression. And the shear, it's still clockwise, So the shear is actually still in the same direction. It's okay. Numerically, it works out.
Okay.
If you had sliding other linear shear forces like we did on the pipe example, where they are the same everywhere, you then have to pick a plus or a minus, and they're going to add on one side and subtract on the other. So I guess mathematically the principal stresses end up with the same result. Because that's at 6 p.m., I guess I say it's the same. The drawing is like that, but the principal stress values you would get are the same. Does that mesh better?
I'm just trying to imagine it looking at it, if we were to look at it from the end of the pipe or whatever. Yeah, like that.
Mm-hmm.
So then the compression and tension would be coming at us, right?
That's correct.
But then your torque would be going around like this.
Right, and so it would be
So
in
it's,
a plus X direction this way and
oh,
a
about
minus.
X is what you mean.
Right.
Yes, all right.
Right. That it is clockwise everywhere,
I was just
or it
looking
is.
at your arrows.
So then this is your sigma x, sigma y, tau xy stress state that you would then put in and get sigma A and sigma B. So this is arbitrary stress state. And then from this, you go up and do this to get principal stresses. And that is it.
Are we gonna have like a practice test?
Nope.
Will you pull up the exam 2 solutions on Blackboard?
Yes, I absolutely will. I did not, I should have already, but yes. Exam 2 solutions will go up. I do have a short additional set of a few practice problems, but I don't have a full-on practice final. So I am posting exam 2 solutions. I am posting the couple more, and mostly they're combined loading problems to practice. And I'm posting the sheet that is the reference stuff that you will have, so that you know if it's not on that sheet, it needs to be in your brain.
And what day is our time?
I don't remember. One of them, yes, both of them are next Wednesday. One's 8 a.m. and one's 2 p.m. And I guess you guys nominally are the 2 p.m. one. I do have, and it is in here. It is not in the lab room. It is scheduled to be in here. If you would, for whatever reason, like to take the 8 a.m., there are a million seats in that room. Just let me know that you want to, so I show up with the right numbers of pieces of paper. So email me if you want to take the 8 a.m. on Wednesday, and that would be fine. Just the early slot on the same day.
Question on